All right, the common ion effect in solubility. It's the common ion, right? It suppresses, well, it shifts equilibrium, right? So if you have a common ion, it shifts it in the direction away from the common ion. So if I have a common ion in solution, it's going to suppress the solubility of the ionic compound. So for example, if I compare the solubility of silver bromide in pure water versus a silver bromide in a 0.001 molar sodium bromide solution, uh, the sodium bromide is going to suppress how much silver bromide goes into the solution. So the bromide ion, is the common ion here, right? So if I have a concentration of bromide ion already in there, it's going to shift the equilibrium back towards the solid, and you're going to lower the silver concentration. So in pure water, right, when this breaks apart to form X amount of silver and X amount of bromide, X times X is X squared, set it equal to the KSP value, solve for X, and this is the solubility of silver bromide in water. When you've got the common ion, you're starting out with a whole bunch of bromide in there. So it's going to lower the silver concentration. So it's no longer X amount of silver and X amount of bromide. That's gone. You've got a whole bunch of bromide in there, and that's going to make the amount of silver in there much smaller. So divide by both sides by 0.01 and solve, and you get much less silver ion going into solution. All right, pH and solubility. So if you've got something like hydroxide is your polyatomic ion that's in your insoluble uh, solid, uh, putting an acid in there is going to make it more soluble. Putting hydroxide in there is going to make it less soluble. So if you put a bunch of hydroxide in there, it's going to suppress, how much magnesium hydroxide solid is going to ionize. So at a buffer of 10, uh, we know what the pH is. Subtract from 14, we therefore know what the pOH is. And if I take the pOH and take it to the base 10, I can get the hydroxide concentration. All right, so I plug that in and solve for chromium, right? The chromium concentration is going to represent how much chromium hydroxide is going into solution. So they are. Molar solubility at a pH of 10. So the common ion hydroxide is suppressing how much of the chromium ions go into solution. All right, so if you've got magnesium hydroxide, if you put this in an acidic solution, you're going to increase the solubility of the magnesium hydroxide because you're going to neutralize some of that base, right? You're going to take it out of the system. The system respond to try to replace it. All right, salts of weak acids are more soluble in acidic solution than pure water because the anion will react with the acid. All right, so if I've got anything other than one of the ions associated with the strong acids, H plus is going to react with that conjugate base. So if I have barium fluoride, fluoride ion is the conjugate of hydrofluoric acid. So if I put H plus ion in there, it's going to be a spontaneous reaction. That fluoride ion is going to be taken out just like hydroxide would. And it's going to shift the equilibrium towards the barium ion concentration side. So you're going to increase the barium concentration. A complex ion is an ion containing a central metal cation bonded to one or more molecules or ions. So just like when we had acids being added to solubility equilibria where you had hydroxide, where the acid would react with the hydroxide and drag the reaction forward, making the insoluble hydroxide more soluble, or we had a conjugate of a weak base that the acid could react with and make the ionic compound more soluble. We're going to do the same thing, except this time we're going to be complexing the cation, all right, with Lewis bases. So for example, when you have copper 2 ion and you introduce it to ammonia, what happens is 4 ammonias covalently bond to that copper 2 and create a copper ammonia complex. So notice this is then a redox reaction, right? Ammonia is a neutral molecule, copper 2 is plus 2 charge. So on those 4 ammonias covalently bond. It's a weird thing, right? Covalently bonding with a copper ion. This whole big molecule now has a plus 2 charge. And a lot of times you get a color change with complexing. So this is the cool thing with complexes. You get a color change. All right, so we've had Kas, Kbs, Ksps. Now we have Kf. And notice, right, when we complex 1 mole of copper with 4 moles of ammonia to make 1 mole of the complex, we've got a really big K value. So these are spontaneous reactions, these complexing reactions. So copper with a plus 2 charge, you get 4 covalently bonded ammonias to that, and the whole thing now has a plus 2 charge. So again, it's a covalent bond between the cation and the Lewis base. So a complex ion is formed by a Lewis acid-base reaction. The metal ion is the Lewis acid. The neutral molecule or anion acts as a Lewis base, called a ligand, right? So when you have these complexing where you've got these Lewis bases attaching to the Lewis acid, we talk about how many ligands are attached to the Lewis acid. And we talk about a coordination number, right, representing how many ligands attached to the cation. It's a covalent bond between the Lewis acid and the Lewis base, right? So we got coordinate covalent bonding, right? Thus the coordination number, right? So we've got both the electrons being donated by the Lewis base to form the bond. And we have a K value, right, which are usually large. These are spontaneous reactions. Again, products of a reactants raised their stoichiometric coefficients is equal to Kf for the formation of this complex. So if I have a plus 1 charge, typically you end up with 2 ligands attaching to that plus 1 charge, right? So silver ammonia complex, you get 2 ammonias attaching to the silver ion, and you have a large Kf value. If you've got a plus 2 charge, typically you end up with 4 Lewis bases attaching to the thing with the plus 2 charge, the cation with plus 2 charge. And notice, right, if copper has got a plus 2 charge and you've got 4 cyanides, which are anions with a negative 1 charge, right, 4 negatives and 1 2 plus adds up to a 2 minus on the complex between cyanide ion and copper. If you've got a plus 3 charge, typically you can have 6 ligands attaching to the thing with the plus 3 charge, or the cation with the plus 3 charge. All right, so as we said, right, we can now take this cation out of a solubility equilibrium by complexing it, and that'll make the insoluble solid more soluble. So here's silver chloride solid on the bottom of the Erlenmeyer. If I add ammonia to this, right, we clean up all that stuff on the bottom by complexing ammonia with the silver. So the silver ion concentration of the silver ion goes into the equilibrium expression along with the concentration of the ammonia, and the concentration of the complex, the solid is left out. So what is the molar solubility of silver bromide reacting with ammonia? All right, a 1 molar concentration of ammonia. So this is the equilibrium expression for the solubility of silver bromide, right? So we've got this solid in equilibrium with its ions. And what happens when we put the ammonia in, the ammonia pulls the silver ion out of that equilibrium, driving the reaction forward. So we have an equilibrium expression for the solubility of silver bromide. We have an equilibrium expression for the complexing of silver with ammonia. And we can add these two equilibria together to get the overall equilibria of how soluble silver bromide is going to be in aqueous ammonia. So when we add equilibrium expressions, we multiply the K values, and this is how we get the overall K value for this complexing with the solid. So notice, right, the KSP is 10 to the negative 13, the KF is 10 to the negative 7, so this reaction is still going to be non-spontaneous, but more spontaneous in ammonia than water. So when I solve for this, it's the concentration of the complex times the concentration of the bromide, which is being liberated by the solid, divided by the concentration of the ammonia to the second power. The solid doesn't appear in the equilibrium expression. So when I solve for this, you had a 1 molar concentration of ammonia. Since it's non-spontaneous, we can ignore how much ammonia is disappearing, and we can represent X as the concentration of the complex and X as the concentration of the bromide. So when I solve for X, I get how much silver bromide is going into solution by looking at the bromide concentration. If I compare that to pure water, it's way more soluble in ammonia than silver bromide is in pure water. All right, so like we said, if you've got for the AP exam, if you've got a +1 charge on the cation, we can make the assumption that the coordination number is going to be 2 in terms of how many Lewis bases connect up with it. If you've got a +2 charge, we can make an assumption that it's got to have a coordination number of 4. And if you've got a +3 charge, you can make the assumption that it's a coordination of 6. So as you see, there are exceptions, but we can just in general make these assumptions. And here are some of the common ligands, right? Water complexes with cations, right, to form a hydrate. One that's important to us is ammonia. You see ammonia a lot as a complexing. Thiocyanide, cyanide, and we run into chloride a lot. The other ones are there, but the ones that we mostly run into are those.